Hello students, welcome back. In this series of Principles of Agronomy, so far we have covered so many things, and if you have not gone through that, then you can go and check our playlist. So today we are going to discuss about soil chemical environment. We are now covering the soil environment and its impact on agricultural crop production. And today in this particular lecture, we are going to discuss about soil chemical environment and what are the parameters or factors in soil chemical environment that influence the crop growth and how they are influencing the crop growth, right? So in soil environment, if we look at soil environment, suppose this is our plant. Okay, this is the soil layer and this is the plant. So this is the aerial environment, phylospheric environment, where different biotic and abiotic factors affect plant growth, like abiotic factor like wind, rain, then solar radiation, then rainfall, relative humidity. All these factors, they are abiotic factor, and they affect the phylosphere environment. So this is the soil environment, and most of the like water nutrient that is being taken up by the plant through root system or rhizosphere, and that is confined to soil environment. So this is the rhizospheric environment or soil environment. And if we'll look at the study of soil environment and its impact on plant growth, then that is called edaphology. Okay, and a soil environment is basically composed of physical environment, then chemical environment and biological environment. So if the soil microbes, how they are affecting the plant growth, then if we'll study, then that is coming under biological environment. If a soil nutrient status, then soil pH reaction like soil salinity, acidity, if these are affecting how these parameters, or studying about these parameters and how they affect the plant growth, then we have to look into soil chemical environment. And physical environment we have already covered, like soil physical characteristics like soil texture, structure, strength, wall density, soil aeration, then how these soil color, how these factors they affect the plant growth or crop growth and development. Then that is physical environment, and we have already covered about physical environment. Now let's discuss in brief what soil chemical environment is and how it is affecting the plant growth and development. So chemical environment, it comprises of nutrient transformation and availability of different nutrients, and this availability of different nutrients and nutrient transformation, they are affected by soil pH or soil reaction, that is hydrogen ion concentration. Then clay minerals, what is the dominant clay minerals and what are the types of clay minerals found in soil. Then CEC or cation exchange capacity, AEC anion exchange capacity. These are the parameters which affect the nutrient transformation and availability of nutrient to the plant growth. Okay, so see, what is nutrient transformation? Nutrient transformation means there is a continuous cycle going on inside the soil, and where there is process of mineralization, immobilization, sorption, desorption, okay, precipitation, dissolution, all these, reduction, oxidation, all these factors are going on inside the soil. So that is nutrient transformation. Unless and until nutrient transformation will happen in the soil, plant cannot get the nutrient in available form. Okay, so nutrient transformation is essential, and nutrient transformation is depend on the soil pH, clay minerals, C, AEC, etc. So what is pH? Let's discuss one by one all these factors. So what is pH? pH is the negative logarithm of hydrogen ion concentration. So the amount of hydrogen ion concentration in soil it has, if we convert it into negative logarithm or minus log H plus, then that is coming pH. Okay, pH, actually the scale, pH scale was given by Sorensen, SPL Sorensen. Okay, he proposed the pH scale, and pH scale the range varies from 0 to 14. pH influence nutrient availability, soil physical condition and plant growth. So how nutrient availability is dependent by soil pH. So basically the optimum range of soil pH is said to be from like 6 to 7. Okay, so this is optimum. Okay, when the pH is acidic, some nutrient will get deficient, some nutrient will get toxic. When it becomes saline, some nutrient will get deficient and some nutrient get toxic. So pH influence the soil nutrient availability significantly. Then pH influence soil physical condition. If the soil pH is sodic soil, that means if it is beyond 8.5, then there will be dispersion. Okay, so but somehow if some nutrient present like calcium, magnesium, if it is dominant in the soil, then it will become saline, but the soil physical structure will intact. Then plant growth, of course, if this nutrient status and soil physicochemical properties will be disturbed by soil pH, then plant growth will also affected, right? So optimum pH for phosphorus availability in soil, that is 6 to 7. Remember, optimum pH for phosphorus availability in the soil, that is 6.7. If the pH is going beyond 8.5, then there will be dominance of sodium ion, which make the soil deflocculated or dispersed. Okay, so there will be deflocculation when the soil pH will go more than 8.5, then there will be deflocculation. So it is the worst soil physical property, and it is mostly seen in where the soil is dominant with sodium ion. Okay, sodium cation. Then causes for soil acidity, how there will be like soil acidity, how it happens. Okay, so before that, let me tell you, some plants they prefer acidic soil pH. See, acidic soil pH means pH below 7. Okay, neutral soil pH means around 7, and if it is going beyond 7, then that is called alkaline soil pH. And again, in alkaline condition, 7 to 8.5, that is saline, and more than 8.5, that is sodic. Okay, so if those crops which prefer acidic soil pH, these are rice, potato, and tea. Okay, so let's discuss about causes of soil acidity. So if there is aluminum and iron hydroxide hydrolysis happen, then it causes soil acidity. Then leaching of bases, so basic cations like calcium, magnesium, potassium, if sodium, if they are leached down from a soil, then there is like decrease in basic cation, so then the soil can become acidic. Then low CEC. Okay, so if soil acidity is happening, then CEC is also lowering down. So if the soil pH is increasing, then CEC will increase. So it is directly proportional with the CEC or cation exchange capacity. Then if we'll apply acid forming parent materials or fertilizers, okay, if suppose any parent material is having acid forming nature, or any fertilizer is having acid forming nature, then if we're adding that fertilizer to the soil, then also soil acidity might happen. Then decomposition of organic matter, so when organic matter decomposes, there is phenol group OH minus will release, then sorry, H plus will release, and COOH will release. Okay, so that also uh, become make the soil acidic. Then how to ameliorate acidic soil, or how to cure acidic soil? See, when we are talking about saline soil, acidic soil, their curing method is called amelioration. When we when there's any question about amelioration, that means what type of measures you have to take to cure that type of soil. So that is called amelioration. So for acidic soil amelioration, we need liming material. We need to add liming material in the soil. So what are these liming material? These are oxides, then carbonate, okay, carbonate oxides of calcium, magnesium. Okay, so liming materials are oxides, hydroxides, and carbonate of calcium and magnesium. So like calcium oxide, magnesium oxide, calcium hydroxide, calcium carbonate, magnesium carbonate, dolomite. Okay, so these are called liming material. When we add liming material to the soil, it reduces soil acidity and it increases soil pH. Aluminum toxicity reduced by liming and submergence. So when there is aluminum toxicity in the soil, then if we add liming material of, okay, aluminum toxicity is mainly you can find in acidic soil. So when we are going for liming or addition of these materials, which we call liming material, then there is reduce of aluminum toxicity in the soil. And also by submergence we can reduce the aluminum toxicity. Submergence increases the availability of phosphorus, iron, and manganese. So how this happen? So basically, when there is submergence of the soil, then the soil pH, whether this is acidic soil or saline soil, that tends to go towards the neutrality, and towards the neutrality, soil phosphorus availability will be higher. So that is the reason how in acidic soil, if we'll go for submergence, phosphorus availability increases. Then iron and manganese, they are more available in reduced condition. That means Fe2 plus and Mn Fe2 plus and Mn2 plus form. So These are the reduced form of iron and manganese. So when we are going for submergence, then there is the iron and manganese, they come to reduced form. From oxidized form they come to reduced form. Why they come to reduced form? Because this is the submergence causes the reduced environment, right? Then so it was about the acidic soil, and in detail we have discussed in our previous lectures, like whatever we have uploaded in our channel. So you can go and check that for detailed lecture about acidic soil and its amelioration. Now alkaline soil. Okay, alkaline soil, what is alkaline soil and how to ameliorate it? So alkaline soil means if the pH of the soil is greater than 7, then we can call it alkaline soil. So there are different types of alkaline soil, like saline soil. When the pH, so this is important, okay, you have to remember it. For saline soil, the pH is less than 8.5 EC, that is the electrical conductivity, which unit is decisiemens per meter. It should be more than 4 decisiemens per meter. ESP, exchangeable sodium percentage, that is less than 15. Saline alkaline soil, both all these three parameters like pH, EC and ESP, they are higher, like more than 8.5 pH, EC more than 4 and ESP more than 15. Alkaline soil, the pH is more than 8.5 but EC is less than 4, because in alkaline soil you can find the dominance of sodium, like sodium carbonate, sodium bicarbonate, but here the soluble salt concentration is very less. Okay, soluble salt concentration means calcium chloride, magnesium chloride, calcium sulfate. Okay, so this concentration is very less, so that's why it is the EC is, or electrical conductivity, is less. Okay, so EC is decisiemens per meter at 25 degrees Celsius, measures the salinity. ESP is the exchangeable sodium percentage, and it is the degree of saturation of sodium in exchange complex. So out of total cation exchange capacity, how much percentage is taken by sodium? That is ESP, exchangeable sodium percentage. Now, how to reclaim alkaline soil? How to reclaim alkaline soil? So we know, alkaline soil are of two types: saline and alkaline alkali soil. So saline soils are reclaimed by leaching. Okay, leaching means excess water we have to put in the soil, so that will leach down the excess soluble salts. Because how leaching can be beneficial in saline soil but not in alkaline soil? Because in case of leaching, the only the soluble salts can go beyond the root zone. Okay, so when we are adding excess amount of water along with the percolated water, some soluble salts which are soluble, and you mostly find soluble salts in the saline soil, not in alkaline soil. Because in alkaline soil we generally found sodium, sodium carbonate, sodium bicarbonate, sodium, these salts are not soluble in the in water. Okay, now, alkaline soil, for reclamation of alkaline soil, we need to apply like gypsum, calcium chloride, sulfur, elemental sulfur, sulfuric acid, iron sulfate, FeS, ferrous sulfide. So these are the reagent like gypsum, calcium chlorides, elemental sulfur, H2SO4, iron sulfate, FeS, ferrous sulfide. These are the reagent or ameliorant which are used for ameliorating alkali soil. Now this was about saline alkali soil. Now what about clay colloid? Okay, clay minerals. So clay colloid are of two type. One is organic colloid and inorganic colloid. Organic colloid example will be humus, and inorganic colloid there are silicate clay minerals and non-silicate clay minerals. Silicate clay mineral like kaolinite, that is 1:1 type clay mineral. Montmorillonite, vermiculite, they are 2:1 type clay mineral. Then chloride, that is 2:1:1 type clay mineral. So what does this 1:1 represents? That is, see, silicate clay mineral composed of two types of layers or silicate layers. Okay, one is silicate layer, one is silicon tetrahedral layer. So one sheet will be silicon tetrahedral layer, another sheet will be aluminum octahedral layer. Okay, in soil chemistry, in soil science part, we will cover in detail. So when one silicate layer is attached with one aluminum octahedral layer, then that is called 1:1 clay mineral, that is kaolinite. When two silicate layer will be there and followed by one aluminum octahedral layer, okay, then again two silicate layer, then that is 2:1 type clay mineral, that is montmorillonite, vermiculite. Then 2:1:1 means it is impregnated with other layers, then that is 2:1:1 type clay mineral, and the example is chloride. Then non-silicate clay mineral examples are geothite, that is Fe2O3.H2O, gypsite, that is aluminium Al2O3.3H2O. All of hence these are non-silicate clay minerals. See, in soil, the cation exchange capacity is having very significant role than anion exchange capacity, because in soil mostly cations they play the significant role. Okay, so CEC is very its extent or density or dimension is very higher than anion exchange capacity. So CEC influences the capacity of soil to hold nutrient and principal buffering mechanism in soil. So CEC contribute to the buffering nature of the soil. Okay. Now, how nutrient transformation happen in the soil? Nutrient transformation in the soil. So whatever so far we have discussed, they are affecting the nutrient transformation. So now we are going to delve into nutrient transformation. Okay. So how nitrogen transformation mechanism happens? So basically, the major source of nitrogen in soil is organic matter. Okay, soil organic matter. Organic matter means the plant residue is falling on the soil. Then we are adding different organic, bulky organic manure. Okay, so this is the major source of soil nitrogen. So organic matter as such cannot provide nutrient to the. I mean, as such it is not available to the plant. So it has to be decomposed. It has to be simplified. So that simplification process is known as mineralization. What is mineralization? It is the formation of nitrate and ammonium, and these are the available form of nitrogen from organic matter. Okay, so when organic matter convert to nitrate available form like nitrate and ammonium, that is called mineralization process. For mineralization process, optimum moisture of the soil should be 50 to 70% of water holding capacity, and it is higher in high temperature. And when mineralization happen, when the CN ratio of the residue is less than 20:1. Okay, now see, I was talking about this. Organic nitrogen is very significant, higher significant than inorganic nitrogen. Then how urea hydrolysis happens? So when that is a major fertilizer what we are applying in the soil, that is urea. Urea, the formula is NH2CO NH2 NH2CO NH2. That is you know that is the formula of urea, or empirical formula of urea. So when we are applying urea in the soil, that combines with water, that is soil available moisture, then the urease enzyme acts on it. Urease enzyme, the major component is nickel here. So urease enzyme, after acting of urease enzyme, it converts to ammonium carbonate, that is NH4 whole to CO3, which is unstable, and it further converts to ammonium NH4 plus and carbon dioxide. So what is the fate of this ammonium after conversion of urea to ammonium? What is the fate? It can be absorbed in clay complex. Okay, so urea is basically a cation, and clay mineral that is mostly anionic in nature. So it adsorb, like, I mean, negative ion will attract no, positive ion or cation. So it will attract and it will hold that ammonium. Okay, so ammonium fixation is somewhat might be some problem in some soil. Okay, then another fact is it can be uptake by plants. Some plants they prefer to uptake ammonium instead of nitrate. So urea can be ammonium can be taken up by the plant. Then losses by volatilization. Okay, if the pH is higher and if the temperature is higher in the soil, it will lose through volatilization. Then it can convert to nitrate through nitrification. So ammonium is a substrate for nitrification. So if the soil is acid, like, I mean, aeration is proper, so it will convert to nitrate, NO3 minus. Okay, NO2 minus, then NO3 minus. So that is the process of nitrification. First nitrite will form, then nitrate will form. So the bacteria here involved is nitrosomonas and nitrobacter. Then urea is highly water soluble and leachable. So you have to be very careful about urea application. Hence recommended for incubation in soil for 1 to 2 days before application. Okay, so it has to be incubated in the soil. That means it has to be, you just take directly, do not apply the urea in the soil. So you just take some FYM or soil. Okay, then incubate this urea whatever you need to apply. Then after incubation for few days, then you can go for application for better you know absorption and all. Recommended in acidic or neutral soil, not in alkaline soil, because in alkaline soil volatilization problem might happen. Okay. Now different losses in native and applied nitrogen. There are, see, nitrogen is a very versatile nutrient. I mean, it is very prone to loss. So there are different losses mechanism in nitrogen, like volatilization loss, leaching loss, denitrification loss is there. Then fixation might be a problem, like ammonium fixation, and immobilization is a problem. So volatilization, when it happens, volatilization is a chemical process. It happens when the pH is higher, CEC is very less, temperature is high, more calcium carbonate, more nitrogen dose is there. So these are the factors affecting the volatilization. Major component is higher pH with higher temperature. If it is there, then volatilization can happen, might happen. Okay. Native alkalinity or externally induced alkalinity is necessary. See, externally induced alkalinity means if you are applying more, alkaline forming fertilizer due to increase in alkalinity due to hydrolysis, then it might also happen. It might also trigger. Okay. So what happens here? Ammonium plus H2O. So it dissociates into NH3 plus, which is a gas, and it liberates to the atmosphere. Right. Then leaching is a physical process. It is just a physical process. There is no chemical transformation happens. There is no microbial transformation happens. So leaching is mostly dominated in nitrate forming fertilizer, and if there is soil, nitrate is there, because see, nitrate is a cation, like cationic combination. So NO3 minus, right? So cations and soil clay mineral is cation, so it will repel each other. So it is highly mobile in soil, nitrate. So when we are adding excess amount of water or there is excess amount of rainfall, so these nitrates, they are not get fixed by the clay mineral, right? So they will easily leach down. So that is called leaching. A submerged soil with less CC will trigger this process. Then split application recommended. So when there is leaching is problem, like if the soil is sandy in nature or light texture in nature, then we can split that urea into 2 or 3 parts in the crop growth. Okay, so that is how we can reduce the leaching loss and we can increase the nitrogen use efficiency. Then ammonium fixation. So it is basically trapping the ammonium in the soil. So mostly these 2:1 type clay mineral like montmorillonite, vermiculite, illite, they fix ammonium. Okay, mostly this type of silicate clay mineral, they fix the like ammonium in the soil. Uh, See, ammonium fixation and immobilization, they are actually there is no loss in this process, but it fixes the available nitrogen, and it reduces the availability. Immobilization, when it happens, it is microbial process, and basically it is the temporary locking of available nitrogen in the soil. So when it happens, when the CN ratio is going beyond 30:1, then more carbon is available. So to consume more carbon, more microbes will grow there, and these microbes, for their body synthesis or protein synthesis, they will trap the available soil nitrogen in the body. Okay, but that is temporary in nature. Then phosphorus transformation. This was about nitrogen transformation in brief. Then coming to phosphorus transformation. In case of nitrogen, we just see कि organic nitrogen is having significant impact in soil nitrogen availability than inorganic nitrogen, because the extent of organic nitrogen is higher in soil. But in phosphorus, it is opposite. In phosphorus, the inorganic phosphate is more than the organic phosphate in soil. So basically, two forms of phosphorus is available for plant growth and development. That is primary orthophosphate, that is H2PO4 minus, and secondary orthophosphate, that is HPO4 2 minus. Remember, primary orthophosphate, that is H2PO4 minus, and secondary orthophosphate, that is HPO4 2 minus. Okay. In acidic soil, the phosphorus is fixed as aluminum phosphate and iron phosphate, but in saline soil it is fixed as calcium and magnesium phosphate. So we have already talked about pH. So pH, when it is agricultural neutral, that means 6 to 7, then the phosphorus availability will be more. If it is acidic soil, the phosphorus will be fixed as aluminum phosphate and iron phosphate, and in case of saline soil, the phosphorus will be fixed as calcium and magnesium phosphate. So there will be reduction in availability. In vertical, the form of phosphorus, the fixation is calcium phosphate. In alphisol, it will be iron phosphate. So it will reduce the phosphorus availability. Phosphorus fixation is influenced by soil pH, nature and amount of clay, which type of clay is present and what is the extent of its content, free oxides of aluminum and iron, calcium carbonate, organic matter. So these factors will affect the phosphorus availability or phosphorus fixation. High fixation in clay, like clay soil than sandy soil or loamy soil. Then black soil will also fix higher amount of phosphorus. Then vermiculite and montmorillonite, like 2:1 clay mineral, they also can fix more phosphorus in the soil and make them unavailable. FYM certain period of fixation. If when we are adding excess amount of FYM, then it will shorten the period of fixation. Then phosphorus deficiency largely seen in red soil, because in red soil mostly iron is dominated, and iron, it will make iron phosphate, and it will bind the available phosphorus, uh, and the phosphorus deficiency can be observed. Then manual phosphorus or manure phosphorus, that means when we are applying phosphorus through manure, that relatively that is more labile than inorganic phosphorus, because inorganic phosphorus is prone to different type of fixation or precipitation. So manure fertilizer or phosphorus or organic phosphorus is more labile in nature. Phosphorus fixation, if you'll see in different clay mineral, it is higher in alphisol, followed by vertisol, followed by inceptisol. All phosphorus fractions decreases with soil depth. So when we go down to the soil profile, then all phosphorus fraction decreases. Okay. Then there is a parameter called phosphorus fertilizer sensitivity index. Phosphorus fertilizer sensitivity index, that is grain yield with no phosphorus. That means how sensitive the phosphorus deficiency is for different crops. So what is the formula? Phosphorus fertilizer sensitivity index is equal to grain yield with no phosphorus. That means when we are not applying any phosphorus, what is the grain yield we are getting? And when we are applying with maximum phosphorus dose, what is the yield we are getting? So that is phosphorus fertilizer sensitivity index, and it is highest for sunflower. It is then followed by sorghum and wheat, and it might vary, right? So if the value is highest, that means we are getting grain yield higher relative to the maximum phosphorus application without fertilizer. So that means least sensitive. Phosphorus fertilizer sensitivity index, if it is higher, then the crop is least sensitive to phosphorus availability. Okay. And if it is lower, then most sensitive to available or application of phosphorus. Maize is 2 to 3 times more efficient in phosphorus acquisition than groundnut. Plant phosphorus uptake is positively correlated with concentration of carboxylate in the rhizosphere. Okay, so these concepts we will discuss in detail in further lectures. Then potassium transformation. Another major nutrient is potassium, and let's discuss about potassium transformation. So there are four forms, major forms of potassium. One is mineral form or lattice form, that is mineral potassium, and this is in highest concentration in the soil. Then another form is non-exchangeable form. So from mineral form, it converts to non-exchangeable form. Another form is exchangeable form, which can readily available, as well as exchange to soil solution form. Another one is soil solution form. So basically, in potassium triangle, we can see the active participation of these latest three forms, like non-exchangeable form to exchangeable form to solution form. Exchangeable form, to get the like exchangeable potassium, we use generally one normal ammonium acetate. So basically when we are analyzing soil available potassium, basically we are using exchangeable potassium. But in solution potassium, we can use hot water to extract the excess potassium from the soil. All are in see, potassium generally it is not found deficient in soil, because this potassium, there is a well established equilibrium state. All these form of potassium, they are equilibrium state. So if there is less or reduction in non-exchangeable form, then from mineral potassium or lattice potassium, it will come to non-exchangeable form. So if there is exchangeable potassium is deficient, then from non-exchangeable potassium it will convert to exchangeable potassium, again to solution potassium. So there is a well balanced form that is called potassium triangle. Okay. Next, some important questions let's discuss about that. Like, what is cutans, CUTANS? These are the common fabric features in soil and represents for foci of chemical and biological reaction. So that is a common fabric structure where chemical and biological uh, actions are mainly happening. Important source of calcium, then calcium is a secondary macronutrient, and important source of calcium like dolomite, that is calcium magnesium carbonate, calcite, that is calcium carbonate, apatite, calcium feldspar. These are important source of calcium. Important source of magnesium like biotite, dolomite, chlorite, serpentine, olivine. These are important source of magnesium. Sulfur is present as sulfide, sulfates, and in organic combination with carbon and nitrogen. So mostly nitrogen as well as sulfur they present in organic form. Next, some micronutrient like iron. Iron is most abundant in metallic element like in earth crust. Most abundant metallic element in earth crust is iron. Okay. Before that, like oxygen, silicon, these are the major nutrient present in earth crust. Iron is deficient in calcareous soil. Remember, iron is deficient in calcareous soil. Then well aerated upland soil also iron is deficient because iron is mostly available in reduced condition. And soil with high phosphorus content also iron is, you can find deficient because phosphorus iron they are like antagonistic in nature and they will fix each other. Okay. More soluble and available in ferrous form, we have already talked about it because in reduced condition iron is converted into ferrous form, that is a Fe2 plus form, and it is mostly available to the crop. If we are adding more organic matter, then also iron availability improves. Okay, addition of organic matter improves the iron availability. Next one is manganese. This is also one micronutrient. It is chiefly present in oxide, carbonate, and silicate form. Secondary mineral like pyrolusite and magnetite also contains manganese. Exist in divalent form, trivalent form, and tetravalent form. Okay, and availability increases in acidic form and in submergence condition because manganese also present in available more available in manganese form, but decreases with addition of organic matter. See, iron availability increases with addition of organic matter, but manganese availability decreases with addition of organic matter. So these are the few distinction how you can answer in the examination. Then what about copper? Copper is mainly available or mainly present in the form of sulfide, but most abundant is chalcopyrite, that is CuFeS2. Solubility of copper decreases with rise in soil pH. Solubility of copper decreases with rise in soil pH and strongly fixed on organic matter. So copper is also strongly fixed in organic matter. Manganese is also strongly fixed in organic matter. So when we add organic matter to soil, copper also you can find in deficient condition and manganese also you can find deficient. But these are temporary. And what about zinc? Zinc found in sphalerite, ZnS2, and other forms are also available. Zinc deficiency is high in high pH soil, high organic matter, again zinc, higher calcium carbonate or calcareous soil also zinc availability is less because in calcareous soil also it fixed as or precipitated as zinc carbonate. Then what about boron? Boron is present in soil mineral like tourmaline, okay, which is a fluorine bromosilicate, and it is very resistant to weathering. Boron applied to soil mostly soluble in acid soil. More than 72% water soluble boron converted to insoluble at pH 7.5, more than 7.5. So when we are going beyond pH 7.5, mostly it forms it precipitates, okay, convert into insoluble form. Leaching is boron leaching is a problem and it is high in light texture soil. Then molybdenum. As molybdenum is present in MoO4 2 minus in soil, that means it is in available form like MoO4 2 minus form. Its availability higher in higher soil pH. Molybdenum availability increases with phosphorus fertilization and decreases with sulfur. Then chlorine. Chlorine is present in soil as chloride form, Cl minus form, that is Cl minus, and it is highly mobile in soil. And mostly chlorine deficiency is not found in Indian soil. Then organic matter increases the availability of iron and boron, but decreases the availability of manganese, zinc, and copper. So we have already talked about it. Okay. Now acidity increases availability of iron, manganese, and copper. Alkalinity increases the availability of molybdenum. Calcareous soil decreases the availability of zinc and manganese. Phosphorus availability increases with availability of molybdenum and decreases with availability of iron and zinc. So there is a synergistic relationship between molybdenum and phosphorus, and there is antagonistic effect of iron and zinc with phosphorus. Then submergence increases the availability of iron, manganese, and molybdenum. These are very important. You have to remember all these things, like these points. Then next one is soil biological environment, what we are going to discuss in next class. So stay tuned, and if you have any doubt regarding any concept from this lecture, you can let me know in the comment section, or any part from agronomy or soil science. If you have doubt on any part, you can let me know. Okay, see you then. Keep studying and keep signing.